So over to you, Keith.
Hi, everyone. So I'm going to talk about TLDK, the Transport Layer Development Kit, for short, TLDK. All right. Memorize that. Okay, so really, the Transport Layer Development Kit, conceived by a number of people, is we're trying to build a set of libraries and a set of functionality that will give us a transport layer support within TLDK or VPP or wherever we put it. Right now, TLDK is housed underneath FIDO as one of the projects, FDIO. And it will work with VPP and DPDK when we get done. So it's all open source at this point. We're just going to be doing the layer 3 protocols like UDP and TCP. Of course, we're probably going to do others as well. But we also need to work on the layer 2, layer 3, which VPP currently provides, but there might be others that will do it for that don't support VPP if you don't run VPP. All the code is open sourced, of course, and you guys all know this stuff, so it's freely available. You don't have to pay anything. Just sign up, probably a Linux Foundation free account, and you can download it. You may be able to download it without that account, I believe. You just need to go to the Tweaky pages here and find it. Get that out of the way. So they told me I only had a half hour, but they wanted me to stretch it to an hour, so just for Craig. So it's a set of C libraries, and we're going to try to maintain it in that fashion. There may be some AVX instructions that'll fall into that range. I know DBK does have some today, so those may be supported at one point. The primary 2 protocols today are going to be UDP and TCP. The current one we have is UDP in the source code up there right now. So the real goal is to create a very high-performant TCP stack with purpose-built applications. We're not necessarily trying to improve the performance of, say, a Linux native application or any socket application that you may want to put on there. First cut, we may not have sockets, but we are trying to look at adding sockets and also be able to support a native binary and like an LD preload in fashion. But right now, our real goal is to make the best high-performance stack you can come up with. So, whenever we build this thing, we're going to have a set of libraries that'll come down to how the application is built. And I think I have another slide to that. Right. So, in normal network stack designs, it's one packet in, one packet out type mentality. It's also all the packets are driven from the I/O through the network layers all the way to the top to the application and hang on a queue, typically a socket queue, waiting for the application to come by and say, yes, I want this data, let me go process it. We don't want to do that because for one thing, we do all that work, then all the caches will get cold waiting for the application to come by and pick up that data. So what we want to do is move the packet as quickly as possible to the core that will be processing that packet and not do the protocol processing until the application actually asks for the data. Then we'll do the protocol processing on that packet. Now that's kind of an upside down view of how that's done, but at least it keeps all the caches warm and it's a kind of just-in-time type mentality. Now what we're going to do also is drive multiple packets to the stack at one time, not just one at a time. And that's a big win if you know what DBK and VPP. They're vector processing, which is similar to DBDK's methodology of an array of envelopes. That's how you gain the performance and that's how you amortize the cost across multiple packets at one time. Now, in this particular case, we're going to use hardware to try to push those packets to the cores as quickly as possible with filtering and various other staging to get it done. And that really is going to be the key factor. Try to utilize as much hardware as you can to get the packet to the right spot And then the application can then continue to further process that packet. Now this is kind of a really big block view of how this works. So you can see we have a physical layer, we have DBDK, we have VBP. Now you can have VBP or DBDK. You can have both if you like. And we're hoping to put TLDK and allow it to run with this environment with both or one or the other. Now the control plane we aren't dealing with yet, but we do have to have some configuration and support for that, right? If you're building a stack, you have to have that type of management support. Now the application in this particular case is, I'll call it a purpose-built application. It's built for this environment. It's built for the TLDK stack, and it'll use those APIs. So if you want to take your favorite socket application, you're going to have to rewrite it. And it's going to be a bit difficult to do because this is still a run to completion environment. Is there any questions on that page? I know it looks nice and simple, but... Okay. So the next thing we want to look at is we would like to add a full TCP and UDP stack, or what people might consider a real stack in here. And we want to put in a socket layer, and we do want to put in a socket preload layer, just so that we can get some native applications. Now those native applications running through socket preload don't expect a big performance gain. Even the ones running within the same address space on top of a socket type layer don't expect a big performance gain. It should be better, but it may not be the best. We're really focusing on the pre-built TLDK or purpose-built TLDK applications. Any questions here? Kind of going a little fast here. So they want me to turn this into a 2-minute presentation. That's what they said. I said, no, I want 3. Trying to push back, you know. Anyway, this is the actual APIs, and you can see in this particular 2 slides here that I've written the most complex application I can come up with in these two slides. And it's probably the most complex thing I've ever worked on. So really what we're doing here is these are the APIs. We have a create, a destroy, an add device. And then we have our delete device, of course, if you're going to use it. And we have the RX bulk and TX bulk type APIs. And we also deal with the streams. Now in this particular case, these are UDP streams. You'll have a similar API for a TCP stream. And so what you'll do is you'll create those streams, or create your context, then create your streams, and then do receives and transmits in that environment. Now I've added some little variables down here for the next, because it wouldn't all fit on one page without micro text. So make sure you memorize those. We'll go on to the next one. So here's the most difficult program I've ever written in my life. It took me days. So in essence, all we're going to do is create a device, a context, add devices to it, open up the stream for UDP. Now there's some parameters and pieces that have to be filled in before you can open the stream, but I'll leave that up to you much more educated people than I. Then you'll go into your infinite loop like you do typically in DBDK, reading multiple packets, calling in and the transmit side, and I forgot to put in the actual processing of the stream itself. So, but you'll actually deal with those packets. So this is the simplest form that you can come up with, right? So you can see that it's still a very simple set of APIs, but we're trying to make it so that the packets that you process right then and there are dealt with right then and there. So that you can keep the caches warm, you don't have to worry about all that processing, and hopefully get better performance in that. And whenever you're all done, you'll just close the stream and probably close the context, which I didn't put in there. Okay, any questions there? It's pretty simple.
This application, I've got a lot of fundamental problems with the TCP user space, but one of the ones here is that the pole mode model of DPDK is fundamentally wrong for a endpoint-based application.
For some endpoint application.
Almost every endpoint application.
I disagree with you there, Steve, but go ahead.
I mean, because an application wants to block for data. Unless you want to start to build yet another user mode, thread library, scheduler, you're going to...
Well, we do have a thread library, but we're not necessarily using it in this context. Think of this as more like a proxy or something like that in that particular case. If you want to wait for data to show up, you're going to have to block.
We already have problems today where people dislike terribly burning 100% CPU resources when nothing's happening. It gets even worse if you've got cores that are burning 100% CPU resources waiting as an HTTP proxy for the next... I mean, it's great if you're Intel and you're selling CPUs, but it's not very good if you're anybody else.
No, well, you know, in this extremely complex example, I didn't put in the power management pieces that you can call from DPDK, right? And actually decrease your throughput, right?
Well, I mean, I go back to...
you know, I'm not trying to argue the semantics. Some people find that okay, some people don't find it okay to burn CPUs. Because some people don't want the latency hit, some people don't care. So I didn't put it in here, but you can put in the latency and the power management part.
Well, I just hope that, I kind of a person, we grafted onto the DPDK an event-based wait for packet model, which is only partly implemented, not used by anybody. I would hope that you would do that in the API in the beginning for this, as it is a fully supported citizen, and if you want a poll, fine, but otherwise there is a fully available.
There is a what they call the lightweight threads within DPDK. It's in one of the example directories in the power management. You can utilize that and still do this polling, right? But you're going to have to do it at some point to gather your packets. But how you do it, I don't know. You can also then turn on the interrupt handlers within this system to take an interrupt and start polling again, and then go back to sleep again. So there is a way to handle it. It's just not in this particular simple example.
Well, the other problem is that a packet arriving doesn't necessarily correlate with the data unit at a program level. So,
correct.
So all this kind of, you get this weird semantics of, you know, the worst case being crypto, where you're...
Yeah, he wants to talk as well, but anyway, I mean, from this perspective, let's let Ray speak. He's about to fall over.
You know, I think there's plenty of network workloads, not necessarily endpoints, but bumps in the wire in the middle. TCP proxy is one, SSL tunnels are another. On the UDP side, you can think about things like overlay protocols like GTPU, VXLAN. All of these require UDP or TCP support. They're not endpoints, and they benefit from a very highly optimized TCP UDP implementation. So yeah, I take your point on endpoints. Anything that's fundamentally going to block and wait for a packet's not going to benefit here. But it's things in those network devices that are in the middle that need to talk and understand those protocols, potentially you're going to see a big performance boost.
Right, and that's what we're trying to drive here. Go ahead.
Okay. Is it possible to have callbacks, like to have many, like millions of connection? Take it for TCP, for example, with event scheduler, like C-star, something like that. This is the benefit that I see in that model, not to block on one socket, to create multiple sockets in parallel, and a scheduler that mini-schedule many flows. So I expect, so in that case, I would expect callbacks for each. Let's say, hey, I started doing that, and I get callback when the bulk will finish, and the retransmission will finish.
Yeah, and we're really just showing UDP here, and UDP doesn't really require a lot of connections, state, if you want to call it that. But the TCP side would probably have something similar, which you're looking for. And that one hasn't been fully done, and Constantine can tell you a little bit here too. So.
Yeah, actually, I just like to say we have both callbacks and events basically there. So you can choose for each stream, you can choose what you like to have. You can have either callback, that would be basically execute it on the same core where you receive this packet, or you can have just events that would fire, and then you can do the actual send or receive on different core if you like, on the same one. It's up to you.
So if you have an event with an application, you will leverage that, right?
Yeah, sure.
Yeah, that's what we hope to do. I mean, you know, this is a little fragment. We're just starting out. We really want people to help support us and get it where we need to be, but our primary goal is trying to get performance. Now, power, that is something that still can be done. It isn't excluded from here, but it does have some pluses and minuses, and we'll have to deal with that. Now, that doesn't mean that the socket layer that is within the same address space, it will have a blocking semantic, obviously, because that's the way sockets are. But we'll have to figure out how to deal with that, and it'll have to probably be some sort of lightweight threading model. There is, if we go away from sockets a little bit for the private socket layer, because the big benefit is the multi-packet support. We need to drive through that thing, because sockets is inherently, in some cases, a copy, and in the real case, a single packet at a time type interface. But that's what we're trying to get away from in this particular example.
Is the TCP state machine running on the same core as the transmit and receive cores?
Say that again?
The TCP state machine, is it on the same core as the
Transmit and the receive side?
Yeah.
So in this particular case, the receive side is coming into the same core, but we're looking at how we can separate out so we can eliminate some of the DOS attacks, so that we can, especially in TCP, how we can deal with that, and it may be a multi-core solution in that case, because we want to make sure that we can handle the DOS attacks and still process packets in the long run. So that's what we're working on right now. And the transmit side in this particular case probably will come from the same core that processes it as the stack itself. Now, this is some numbers for a very unoptimized system that we did. It's kind of like the first thing out of the box. So you can see here with just one physical core and one queue, effectively to a NIC. We can do 7.4 million packets per second, which is 64 byte frames. And that appears to scale linearly for us currently with the UDP. And that's pretty decent. That's pretty high compared to your other standard FreeBSD-based stacks that are out there. They don't get that high yet. They get maybe 1 or 2 million.
So how do you compare this number against using, for instance, some VXLAN or whatever UDP echoes that you do on top of VPP directly? So let's forget TLDK and you do UDP echo using VPP APIs.
I didn't
which
catch
has a
that,
root.
I'm sorry.
What would be the numbers in that case?
Oh, with VPP in the
Yes, and I think a fair way to compare would be using some VXLAN, for instance, from VPP.
I'm not sure I can answer that right offhand, but since VPP natively can do, where's Ninja? I can't remember what the performance number is. It can do wire rate, typically 64 byte frames at a 10 gigabit link. So if it can do that, then it can at least deliver the packets to the TLDK stack at the right rate. Now, obviously, TLDK has, in this particular instance, with unoptimized code, has dropped the performance down from 14, right? So I think right now it's not so much VPP, it'll be pretty much what TLDK, how can we get the protocol processing down? Because UDP is trivial, TCP is not. So that's where we're going to find the biggest hurdles at today.
A little bit of nitpicking. The numbers are really impressive, 36 million UDP echo per second. But you say max for PCI. That's actually the case if you have only one packet per PCI transaction, but some hardware do not have that dependency and can reach 60 million.
Sure.
So just to make sure that it's not the PCI limitation, that's a NIC limitation.
Yeah, I really meant it to be for this particular system.
Okay, thanks.
Is this one the NIC limitation? Yeah, this is the NIC limitation then, sorry. But it's the PCI implementation for the NIC implementation, right? Or is it? Yeah. Okay. All right, I'll change that so it's actually the NIC limitation you tell me here. He's trying to tell me I only have 10 minutes left. Anyway, so what we have here is all the standard links you can go to and get this code and look at it, and please help us contribute. It is a big project and it is a difficult one, especially to try to solve everybody's problem, everybody's solution, right? And I'm kind of a firm believer of once you decide you need a stack, it isn't that one stack fits all, it's maybe multiple stacks. So, you know, it may be what will happen, but hopefully we can get everything done or at least meet at the 80% rule of everyone's with this one. If we can't, we can't. I'm not going to say this is going to be the one that, the only one we ever see. Obviously there's a bunch out there right now. There you go. I want my 9 minutes. I'm not going to song and dance. Any other questions? All right, thanks.